Okay, right. Sorry for not bringing the right adapter, but luckily somebody else had one. So hello everybody. This talk is in 3 parts. So the first part is what is bad, and the next 2 parts are kind of how to solve it, right? The real slogan of the talk is really use enriched categories, not ordinary categories. But I've tried to make it as a solution to a problem, so hopefully it will be more motivated, right? So the first part is the ouch. So let's explain the ouch. So let's start by surveying some literature. So very often, game models of languages are organized in the form of a category. So here are some examples. So to model a language with ground state, there's a category of arenas and strategies satisfying a visibility condition. You could add other conditions, bracketing and so on. It's not really, all these variations are not so relevant to, it doesn't make any difference, I mean. Or we could have the category without the visibility condition, which is used to model general references. Or we could have the category where the objects are not just arenas, but arenas built on a strong nominal set, and the strategies are equivariant, and this has been used to model good references, right? Not just references, but they satisfy the goodness equations. So each of these is a category. It can be arranged in a category, and it's quite convenient to do that. And each of these is a lot of work to set up. What is the work that we have to do? Well, just to set up a category, what are some of the things we have to do? We have to define the objects. We have to define the Hom sets. We have to define composition. We have to prove associativity. And those are just some of the things we have to do, right? Now, depending on the specific categorical structure, which depends on the language, there might be other operations on strategies and other equations you have to prove, such as unital laws. But really, I'm just having one example of an operation and one example of an equation to illustrate the general point that I'm trying to make in this talk. So certainly, you need to define composition and you need to prove associativity. I don't mean that's all you have to do, but you certainly do need to do that. All right? And then it gets more fun when we start to extend the language in various ways. So we might, for example, extend the language with non-deterministic choice or with probabilistic choice. And when we do that, we suddenly think, well, then of course we're going to have to change the categories, right? The objects will stay the same, but we're going to want to have more morphisms. Oh, things get really complicated. So, in the deterministic case, what is a strategy? Well, you normally define it as a set of finite plays that satisfies a certain determinacy condition. That's a deterministic strategy. If we're going into the non-deterministic world, maybe we want to model May testing, in which case we'll stick with the finite plays, but we'll drop the determinacy condition. Or we might be trying to model must testing, in which case certain divergences and infinite traces will be included. Or we might want to model an infinite trace equivalence, depending on what else you have in the language, in which case you want the strategies to include a whole set of infinite traces, all kinds of possibilities. And then, okay, there should be 2 steps, not 1. Okay. Right, or you might want to be modeling non-deterministic strategies up to bisimilarity instead of trace equivalence, so you would need to define them completely differently. I don't mean that anyone has done this, but you could, I imagine. Right, this is all sort of imaginary work that I imagine could be done, right? Anyway, some of it is real work. What about probabilistic? Well, you could do, for the contextual pre-order on probabilistic strategies, you could use traces, you associate a real number to each finite play. That was done by Danos and Harmer. Or alternatively, you can go down the bisimulation route, and that will be a different notion of strategy. So you've got all these different notions of strategies, right? So look, where does this leave us? Right, it leaves us with this quite disconcerting picture. We had 3 different kinds of game models, right? Different rules about how the players play, with names or with visibility. But we also had all these different notions of strategy: deterministic, non-deterministic, probabilistic over here on the right, which I've left off the picture. Right, so what have we got here? We have m rows, and we have n columns, and we need to construct m times n categories, And for each one, you need HOM sets, you need to define composition, you need to prove associativity, right, for each of these categories. So I remember doing this, I think, for this bullet here. I did a paper on infinite traces, general strategies, and I remember proving associativity, having to work out what to do. It's work to do, and that was just one. Of course, having all this is great if you want to write lots of papers to fill your CV, right? So it has a plus, but it would be nice to be able to do it just once for each row. Okay, so that's the problem. Now, the solution is in two parts, and the first part of this is really going back over stuff which has been studied in the games literature, not exactly games semantics, but certainly games literature. So this is a category called G-bang. It's a Cartesian closed category. Now, secretly, if you're familiar with simple games and the Highland comonad, then you'll see that this is the Coe-Kleisli category for the Highland comonad, but that's a kind of side issue, not really relevant to this talk. I'll just say a bit more directly what this category is, not in full detail, but anyway. So an object is a forest representing a game. So of course any game can be represented as a forest. You start at the roots and you just go down, 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 right? The root is at the top, by the way. Otherwise that description wouldn't make any sense. What's a morphism? Well, a morphism is a strategy for this game. So opponent starts a thread that plays B, and at any time so it's alternating the moves between opponent and proponent. Anytime proponent plays, they can initiate an A thread, or they can continue an existing A thread, or they can play in the B thread. So you get more and more threads, and it's only proponent is allowed to switch between the threads, right? So that's the rules of the game, and that's how this category G-bang is defined. Right? I'm not saying that this is a semantics for anything. It's just a category of games and strategies. And of course, we have all these variations because we can do the same thing. I said it's a strategy. I meant it's a deterministic strategy. But we could vary this category by considering any of these different notions of non-deterministic strategy or any of these different notions of probabilistic strategy. So I've got I've written here 4 different variations. They all have the same objects. The object is just a forest. But in each case, a morphism is a strategy, and strategy is defined differently in each case. Of course, there's a lot of work to do to set up all these categories. I'm not saying anyone has actually done this, right? But one could, hopefully. And each of them will be, I say confidently, Cartesian closed, and they each, since these are all various kinds of non-deterministic or probabilistic strategies, this original category with the deterministic strategy is embedded inside each of them as a Cartesian closed wide subcategory. Remember, wide means it's got the same objects, right? Okay, so we have all of these 6 categories, and the original one, these 6 categories, and they each have G-bang as a Cartesian closed wide subcategory. So how many jobs do we have to do to set these things up? It's a lot of work, of course, but it's n jobs, right? 1 for each. Remember, n is the number of rows, the different kinds of strategies. So we have to do this work for each column. Now, we've done, let's say this is, I think, the end of, right, this is the end of this part, the second part of the talk. Okay, so we've dealt with the columns by setting up these n categories. Now let's think about the rows. So recall, I said that we have m equals 3 categories for the deterministic languages, the OP visible strategies, the general strategies, and the equivariant strategies. Right? They're not all got the same objects. This one has got more objects. Right? And the point I really want to get across is that calling these categories is an understatement because they are enriched in G-bang. I mean, I hope I've worked this out and done it, but anyhow, there should be a G-bang enriched category. And I want to take you through what does that mean, right? Let's go through what we have to do to set up G-bang categories instead of categories. Well, again, we have to give the objects. The objects don't change; they're still arenas or strong nominal arenas in that third case. And then for each pair of objects, we have to give we don't give a HOM set, we give a HOM game, right? And the strategies for that HOM game will be the morphisms from A to B. But we don't just give the morphisms, we first give the game, and then the morphisms come out as the strategies for that game. Okay? So that's the first thing we have to do. So in the case of the OP visible strategies, what will the game A be? Well, you've got an exponential there, so B to the A for arenas. That's the usual way you construct exponential as a function space arena, called by name, let's say. Both players, that should be a lowercase p, definitely, what a disaster. That should be a lowercase p. Both players would obey the visibility constraint, so that's a game, right? And that would be the home game from A to B. And then the strategies for that game, those will be the morphisms. So you're doing a little bit more than you would not do traditionally. Now what about, remember previously we had to define composition and prove associativity. Here we still have to do that, but the meaning is a little bit different because we're dealing with a G-bang-enriched category. So if you think about it, what composition? Composition has to be a morphism in G-bang for each objects A, B, and C. Composition has to be a morphism from this home game times this home game to this home game. That is a single strategy, right? So it's not like it's an operation on strategies, which is what we're used to from traditional game semantics. No, composition is a single strategy. That's a change, but this is required. If we're going to construct a G-bang enriched category, this is what we have to do, right? And for associativity, for any 4 objects A, B, C, D, it's not a universally quantified equation saying that for any 3 categories, the 2 bracketed, the 2 composites are, 2 associated composites are the same. No, we are saying that 2 strategies, the left associated and right associated composite, are the same. So it's equality of just 2 strategies, again, for each quadruple of arenas. So the work that you have to do is different from what you're used to if you're used to traditional game semantics. And of course, once you've done this work, well, you get for free traditional composition associativity because any G-bang enriched category is also an ordinary category. That's a standard fact about enriched categories. So you don't have to, this is an alternative to the traditional work. Okay, so we've gone down the left column of our table, right? We've done M tasks to set up our 3 G-bang categories. And now, for each row, we've given a G-bang category, but we also want a G-bang may enrich category. That should be must. Sorry, another typo. Live on YouTube, right? Of course, I'm much more worried about the people on YouTube disapproving than you guys, right? I imagine you're more tolerant. At least I can see you. So yeah. Okay. So this should be, so for each of our rows, now you're saying this is, what kind of improvement is this? Instead of M times N ordinary categories, I'm asking you to construct M times N enriched categories. So how does this help? Well, there's a principle in enriched category, a very trivial principle, called change of base. So if you have a lax-monoidal functor from V to W, then any V-enriched category is also a W-enriched category with the same objects. And we have an embedding, Cartesian closed embedding, from G-bang, remember the games and deterministic strategies, to G-bang may. So therefore, any G-bang enriched category is automatically a G-bang may enriched one with the same objects, right? Just by change of base. And similarly, we have the same for must. I mean, this is exactly the same story. We embed the deterministic deterministic strategies are embedded in the non-deterministic strategies. And so if we have a category enriched in deterministic, it's certainly going to be enriched in the must non-deterministic. Right? So we don't have to do any more work. And all of the definition of the home games, all the definition of composition, all the proof of associativity, and other operations and equations, you would just adapt to this story to incorporate them. They all come for free, right? So so for each of our rows, so let's sum up. For each of our rows, we defined a G-bang enriched category. That's the deterministic. So we do it all just determinism, right? For each column, we've defined, this is too much. We defined, this is an old version of the talk, sorry. We've defined a category H-bang, and an embedding of G-bang in H-bang, right? So ignore the stuff about comonad because I didn't talk about that. And then, overall, how many tasks do we have? M. We have task for each row and task for each column. We don't have M times N tasks, so it's fewer papers, not so good for the CV, but less work. That's the trade-off, right? So, right. Okay, so if you go back, I want to go back just to say, make this point to emphasize, right? So when I did all this work to prove this associativity, what I didn't realize was that these were two separate tasks that that were sort of mangled together. There was the task of setting up the column and the task of setting up the row. It's quite complicated trying to do those two tasks together, but actually they're separate, right? And so, so take-home message. This is my sermon to you, which of course is, I'm going to ignore myself, but never mind. Right, I'm preaching to you, not to me. So don't say category when you have more than a category, you have a game-enriched category. I mean, maybe, I'm not saying this is always the case, but look to see if it is the case, because if it is, it's worth saying. So put more work in to tell the whole story, to say, actually, this is a game-enriched category. This will pay off, all right? That's it.
Do you have questions? Yeah, Pierre? Yeah.
Thank you. I'm a bit sad because some of my favorite games categories are not in your pictures, like non-alternating strategies, for instance, or concurrent games.
Concurrent games do not fit this picture, sorry. Yeah. But then, I mean, so the things that we did, I mean, if you look at this picture, right? Oh, well, let's go back to the table. Right? I mean, could we if we added concurrent games here, we certainly couldn't do, I don't know how all of these columns could be filled in. I mean, maybe some of them could, but I don't think they all could. Another one that isn't in there is innocent strategies. I mean, that one was left out deliberately. I think that would enrich, but in a different category. So, and then it would not naturally go to the non-deterministic and probabilistic thing, and that's kind of well known that innocence doesn't easily adapt to non-determinism and probability. So innocent isn't in this picture. These pictures all include at least ground state, and they are also all sequential. So yes, it's true, some models don't fit in here, but that's telling you something about the difference between those models and these models. These are genuinely sequential and genuinely alternating, and I mean, the enrichment says the sense in which they are game models, and the other ones are game models in a different sense. I don't know whether concurrent games do enrich in something interesting. Maybe they do.
Okay, thanks.
Are there other questions? We have time for it. Yeah.
Hi. Thank you. Very interesting talk. Very simple question. Is there any notion of evaluation order that we have to have in these strategies? Does it work for both call by name and call by value models?
Okay, yeah, fair question. Right, I sort of presented this sort of in call by name style just because for sake of convenience of exposition, right? So the idea would have to just adapt to whatever you're dealing with. The same idea should work. So if you were modeling call by push value, well, you want 2 kinds of objects and 3 kinds of Hom sets, and but several kinds of composition and a zillion equations to prove. But the idea is the same. The Hom sets will be not sets, but be replaced by Hom games, and composition will be giving a single strategy, and each operation will be replaced on strategies will be replaced by a single strategy. Each equation will be replaced by a single equation. So the idea is the same. I just went for call by name Cartesian closed categories because in these categories, because that's what people are used to, and it's good enough to illustrate the point. As far as these categories are concerned, this is Cartesian closed, so that is quite specific. So you're enriching in G-bang.
I have a question
Yeah.
about associativity. How do you expect the associativity proof to be?
Oh, that's a good question. Okay, I don't know. I think that this is very speculative. Okay, that there could be a nice way of doing this that brings in the two categorical structure from the transition systems over games paper, and that this each thing that should be included in the game story, so operational story, enriched story, all of those bits should be present, and I think they can all be brought together in a suitable framework. And I think maybe these equations could be proved using a two-cell of some kind, but honestly, this is really speculative and I haven't really worked it out. I'm not saying that's the only way to do it, and it probably could be just done by brute force without any of that. But, you know, I wouldn't. But somebody might. Yeah.
Last question.
Thanks for the talk. Are you settled on enriched categories, or how do you look at, for example, other way of having more structures, like maybe double categories or framed by categories? I mean, I like structure, but also it's hard to pinpoint, perhaps.
Okay. Well, in a way, this is relatively close to the traditional way in the sense of presentation, in that the objects are not changing, and all I'm saying is that instead of having a set for the object, make it a game. That's kind of the key point, and then the other changes sort of go with that. I think some of the other structures that people have used, like the ones you're mentioning, honestly, I'm not so familiar with them, but I think they are further away from that traditional package, and that, I think, in some of that at least is a deeper analysis, or I think is a deeper analysis of specific models, whereas this is fairly generic. It would cover a wider range of models, but say less about them, I think. But I'm not really sure about that.
Okay, so let's thank Paul again.
Okay. I don't know. That's,
Okay, so the next speaker is Irmak Saglam. I hope I'm telling it well. And who's going to talk about fair omega regular games.
Okay, hello. I want to start by saying I'm sorry. I didn't look at the previous years, and this is games for verification. So just judging based on how much I didn't understand your talks, I'm hopeful that you won't understand much, so that's why I will give a big motivation and introduction and so on. But thank you. I don't see it on the screen.
Could you?
This? No.
Is it on? Could you check the?
I see. Control center. Maybe somebody else's adapter can check.
Is the laptop connected though? Can you see anything? So it's not connected?
Anything? No. So
How about
maybe you can move on with the next talk. Go on with the next talk and I will put it to somebody else's laptop maybe.
Pardon? Okay.
Okay, maybe you can go on with the next talk.
Yeah, no. That's all right.
Yes.
I swapped your phone.
Oh, sorry.